and the people who played a role in changing astronomy from a just observational method using the human eye as the observational tool. In this period, right in here, from like 1550 to about 1700, telescope technology emerged. People figured out how to make lenses. Those of you who have been maybe to Florence, Italy, there's a science museum there, and one of Galileo's lenses is in the Museum of Science in Florence. And it's a piece of glass filled with bubbles. Glass technology is very mature. It's thousands of years old, but to make it in a form useful for making lenses is difficult. So it's a piece of glass, well, actually maybe like 4 inches in diameter, filled with bubbles, and it looks almost flat, but it has a little magnifying power, and Galileo used that to observe the moons of Jupiter and explain to the city elders that there's another solar system out there. There are these moons. You can see them move if you look over a period of time. You can see that the moons are moving around Jupiter. And he used that telescope to try to convince them that Earth is not the only place with a moon. So anyway, this is a historical chart. It includes some philosophers. There's Kant. But most of this is technical. You can see this explosion here between about 1750 and 1900 in theory of electromagnetic waves, how to build really quality telescopes, some of which could be used today, and the beginnings of understanding the structure and dynamics of the universe. So I leave that for you to look at your leisure, because it's too dense to look at here. Now, I want to tell you that we're spend very little time talking about the solar system. I have a couple of images here to show you. These are the relative sizes of the planets and the sun. That's not where those planets are, but to get them all in one picture, we have the sun on the left, of course, and then there are the relative sizes of the planets. And notice this area here, right? Beyond Mars, these are all gas planets. The recent work on looking at planets in other solar systems has revealed that our solar system is a little weird. Most of the solar systems found elsewhere in our galaxy, it's the exact opposite. The gas planets are closest to the sun, and the rocky planets, if they exist, are out farther. And nobody knows why that's that way. Here's a collection of the moons in our solar system. This is Earth. Now these are to scale. So this is Earth, and then there's our moon. And you see various other moons here. Like Titan, the moon of Saturn, is pretty good size. It has Ganymede from Jupiter about the same size. So anyway, there's a slide or a picture of the moons.
Are the moons gases also, or are they rocky?
They're rocky.
Different.
Titan, there's an exception. Titan is like a big soft pillow. It's so cold where it is that deep inside of Titan there is a ball of liquid, of frozen hydrogen. But the rest of it is gas, fairly dense. And we've actually landed on Titan. You may have seen the pictures where it looks like going out in the desert in western Colorado. You know, there's rocks and things, but they're not rocks. They're chunks of solid carbon dioxide and stuff. So almost all these moons are rocky. They've lost their atmosphere, but not all. Now, this is something we might refer to. This is sort of a family tree for the different kinds of stars that we might encounter in our conversations. And notice it's kind of odd. This is the temperature of the star, coldest on the right, warmest on the left. Just turns out that's an easy way to draw that. And then how bright they are. So there, and then along here, there's a running scale of how long these stars last. So if you go in the upper left-hand corner, these really hot stars, 30,000 Kelvin, 30,000 degrees, a typical one would be 60 times the size of our sun and extremely bright, but their lifetime is measured in, say, 1 million. If they form, they last for 1 million years, and then they burn out. On the other end of the scale, these colder stars, so-called M stars, they're typically smaller than our sun, maybe 1/10 the size of the sun, much lower temperature. They actually appear red if you see one, and they're very dim, but they last for longer than the life of the universe. So this one picture, this is called Hertzsprung-Russell diagram. This captures a sort of, as I say, a family photo of the different kinds of stars that can exist in the galaxies that we'll be talking about. But I want to reemphasize, once we leave this page, we'll be talking in terms of the things that matter in cosmology, which are the galaxies, each of which has 100 billion of these stars. So now this is really the beginning. This is the best picture we have of how our universe began. There's this beginning, commonly called the Big Bang. We actually understand a lot about what happened right after the Big Bang. The Big Bang itself is a topic for the building across the street, I think, or here it's a theological issue about what happened. But let me take you through, in a few minutes, the history of the universe, so we have that as a point of reference in everything we talk about. So we have a Big Bang, and in this band here, which appears white on the screen, the radiation that resulted from the Big Bang was so intense that atoms could not form. So let me remind you of your high school chemistry. Hydrogen, very simple, has a proton as a nucleus and an electron, and they form a neutral object we call a hydrogen atom. But in the early universe, in this band that is white, the intense radiation was so overwhelming that any proton and electron that wanted to get married, a chunk of high energy radiation would come and get involved and knock them apart. And so there were no atoms. It was just an intense bright glow that enveloped everything. But the temperature was dropping. Because the universe was born in an infinitesimally small way, the universe started getting bigger. As it got bigger, the temperature, the average temperature of the universe dropped. And as that happened, the intensity of the radiation in the universe became less important. And atoms eventually could form, and they formed right here. That took about 375,000 years for the temperature of the universe to drop to a point where atoms, so where a proton and an electron could get together and actually have stable hydrogen that could persist. As soon as that happened, the universe became transparent. So we have light sources here. There's a big tube that we're looking at, a fluorescent tube, and imagine yourself inside that tube while that light's being produced. You can't see anything. You're just constantly bombarded by random light coming from different directions. That's the way the early universe was until 375,000 years, and then suddenly atoms formed, and a piece of light that was produced could propagate across the universe without being interrupted. And this green area here, greenish blue, that's the cosmic microwave background I mentioned. We can still see that. It was found accidentally. It's actually predicted in the late 40s and found by accident in the early 60s. And it is a source of enormous information about the early history of our universe. Yes, sir?
how do we know it's 375,000 years? If that, given the way you described that early mass, whatever it is,
Yeah.
is that an extrapolation, or can it be measured? How do we
can't-
get to
can't-
that number?
Okay, it can't be measured, it can't be measured in space, but it can be measured in the laboratory. Because we can reproduce that, what's called plasma, a high temperature so high that atoms cannot form. You can reproduce that in the laboratory. You can measure the temperature at which hydrogen is blown apart by high energy radiation. That's been well established. And like, for example, any kind of scientific experiment that involves hydrogen, if you illuminate the hydrogen with a high enough energy light source, you ionize, that's the term, you ionize the hydrogen. My watch is upset because I didn't give her the code for the Wi-Fi in this building. Take a nap. So the answer is, in fact, let me explain something. At the University of Colorado, there's a laboratory called JILA, J-I-L-A. And JILA is just a name now, but when JILA was formed, it was 4 letters representing 4 words. The Joint Institute for Laboratory Astrophysics. That's the kind of stuff they did there. They did astrophysics in a laboratory, in a little small container. You simulate, artificially build a little chunk of what the early universe was like. And there's lots of different confirmation, different techniques for confirming that the universe became transparent at 375,000 years. So any light source that existed in the universe would produce light radiation, like these bulbs or the headlights of your car, and that light is out in the universe and it can go forever, except there were no light sources. Once the universe got cool enough that atoms formed, and the temperature kept dropping, that the initial glow from the Big Bang dissipated. It's almost invisible now. It can only be seen by using special instrumentation. And so that produced what is called the dark ages right here. Now I'm going to tell you that this scale here is a little bit distorted. This plane here is at 375,000 years. The universe is then dark, totally dark, for 400 million years, because there were no stars. So not only was the original glow of the explosive birth of the universe dissipating, but the universe was getting bigger, atoms had not collected in dense enough clumps to form stars yet. So for 400 million years, the universe was totally dark. But there was something going on, and that's gravity. So you have a hydrogen atom here and a hydrogen atom here, and however small they are, they still are under the influence of gravity, which we talk about a lot more during these meetings. Gravity will draw those 2 objects together. If you get enough hydrogen atoms collected in one spot, the pressure builds, and eventually, if you have a big enough, as this nascent star starts forming, it becomes more potent as a gravitational attractor. So it draws in more and more material. And if the right amount of material is in its neighborhood, you get a big ball of gas. And that ball of gas has a higher pressure at the center than it does at the outside. And eventually, the pressure at the center is enough to get the hydrogen atoms to fuse into helium. And that's a light source. It took 400 million years for that to happen. So total darkness, that's called the Dark Ages. And right here we have the first stars. These are individual stars floating around in clouds of gas, attracting more gas. Different stars are forming. I have some simulations I'll show you in a minute. because that's, by the way, that's a big field in astrophysics, is computational simulation of the formation of stars, galaxies, clusters of galaxies, superclusters, and so forth. Lots of work goes on in those areas. So in summary, we have 375 years of intense radiation and no atoms. Then we start having atoms, and the universe becomes transparent but dark. And this glow, this green area here, we'll talk about that quite a bit. Because, as I say, this is an observable feature of the universe. Numerous spacecraft have been used to measure the properties of that, and it tells us a lot of things about the geometry of the universe and how it is evolved. So, now we're at 400,000 years, and after a while, groups of stars manage to come together, once again because of the influence of gravity, and we get galaxies. And I will show you some pictures of galaxies taken using the Hubble Space Telescope. And they did an interesting experiment. They pointed the telescope at the darkest spot on the sky. They said, actually, there's one guy who had this inspirational idea. Let's just point the telescope at this spot on the sky and accumulate light over a period of weeks. Because it appears there's nothing there. And they did that. And you see a picture emerge. And it's called the Hubble Deep Field. I'll show it to you. And there you see the earliest galaxies. And we know how far away they are. I'll talk about the techniques we use. So we can actually see galaxies, some of the earliest galaxies, and they're kind of weird looking. They don't look like the galaxies that we observe now. And this is a good point to mention, that a telescope is a time machine. When we look at the night sky, or the dark sky with the telescope, we're looking at what the galaxy looked like, or the star looked like, when the light was left that neighborhood. And we're constantly looking at stars and galaxies that are billions of light years away. So that what we see now is not what those objects look like. They may not exist anymore. A star that is 3 or 4 billion years old may be near the end of its life. But we have a time machine. We can look back and see what was happening 3 or 4 billion years ago. So, we have, by the time we get into the universe being 1 billion years old or something, then galaxies are becoming prominent. And as far as we know, there are very few stars just floating around by themselves. Most of them, virtually all of them, are in galaxies. There's big spaces between the galaxies. We'll talk about that. So then we've had this kind of gradual evolution of the universe, galaxies forming, creating new stars. In the densest core of a galaxy, star-birthing areas exist. The stars burn out, they spew out their guts, and that material gets reused deep in the core of the galaxies. And it's an evolutionary cycle. And the reason this shape has this little outward bow, kind of looking like a trumpet a little bit, we'll talk about that. That has to do with the rate at which the universe is expanding, which is a recent development. People used to, well, we'll get into it. I'll get ahead of myself. So now, this picture is hard to read on the screen here. I'll talk you through it. This is a National Geographic piece of art. So if you go online, you can get this in high resolution and zoom in on the areas. But let me show you what it has. Here, in this lower corner here, we're looking at our solar system. Planets orbiting our sun. And then you can see it kind of points to this spot. This is a spot in our galaxy where our star is located. And it has neighboring stars. And if you get the high-resolution version of this from National Geographic, you'll be able to see the various stars that are the neighbors, our neighbors in the solar system. And then if you zoom over to here, we're taking that area and we're pointing right here to this one little area of this thing, that's the Milky Way galaxy. And it has a couple of neighbors, the large and small Magellanic Clouds. And then if you take an even more outward look, you see our local group of galaxies. So the Milky Way, Andromeda, and a few others are in a group. And that group is part of a cluster, or sorry, supercluster. And you're beginning to see here, this is accurate, these kind of cloudy looking areas, those are clusters of galaxies. So there's clusters of galaxies and empty space between them. For example, right here, there's just empty space in there with very little going on. So that's our first look in this conversation about the distribution of galaxies. It's not quite uniform on the scale of our supercluster. But here's a different picture. So here is the Milky Way over here. And this arc here goes out to 600 million light years. So you can see every dot here is a galaxy. So you can see areas here like right there, there's nothing there. But here is a whole bunch of galaxies all together. And then here's another wedge farther out. This goes out to 1.2 billion light years. And this is called the Great Wall. A whole lot of galaxies at about the same distance from our Milky Way. And then there are areas here that don't have much going on. And then we go out to this, 2.5 billion light years out to this distance. And out at that scale, things look kind of uniform. The distance between the galaxies, or the clusters of galaxies, is about the same. So there's a structure to what we observe. Now, the problem is going beyond 2.5 billion light years, even the brightest galaxies are dim at that distance. So we're just out of data when we get over here. And we may do better in the future, build bigger telescopes with more sensitive detectors and be able to add to this census. But I wanted to emphasize that there is structure to the distribution of galaxies that we can see. And I'll say now something I'm going to say over and over. All of these things are moving away from us. And the farther away they are, the faster they're moving away from us. And if you were an observer here on this galaxy, and you looked at the Milky Way, you'd say, hey, the Milky Way is moving away from us. There's no central place in the universe that you say, like the seeds in an apple are kind of near the center. Everybody, every galaxy, every alien out there observing the universe sees everything going away from it. I'll explain how that is possible. So what we are talking about is 100 billion, and I'm using scientific notation here, 10 to the 11th, that's 100 billion. If you're uncomfortable with that, we can have a conversation about why that's a good compact way to capture these enormous numbers. So 100 billion galaxies, each with 100 billion stars. Yes, sir?
When you say there's, on that previous slide, when you say there's structure in the universe, that just looks like kind of a random mess to me.
Right.
It doesn't have structure like a pine cone or a leaf on a tree.
Right. Okay, so let's talk about that for a minute. When I say structure, I mean non-uniformity in the following sense. If you dip your foot in the ocean and have a microscope there and you can see all the water molecules around your foot, they're all equally spaced. There's something compressing them or attracting them so that the average distance between all the water molecules around in the volume of water, they're almost exactly the same. So that's one way there's structure. Another is that